Hello everyone, Mr. Fawcett here, and we are back for part 2 of our lesson on differentiability and continuity. In the first video, we came to a formal definition of what it means for a function to be differentiable at a specific point. In the second video, we're going to go through a few practice problems to apply that definition and really see how that looks and plays out in an AP type question. So we're going to go down to question 1 here, where we have the function g of x. It's a piecewise function. And we have two questions. We're asked if g of x is continuous at x equals 3, and then we're also asked if g of x is differentiable at x equals 3. So as always, I encourage you to pause the video, try the problem on your own, and then come back and see how you did. Okay, so let's think about our three-part definition for continuity first. And again, if it breaks any of these criteria, we can stop and just say the function's not continuous. And if the function's not continuous, we know that's a criteria for differentiability, so we can just automatically say for part B, the function's not continuous, so it's also not differentiable. So for continuity, we first need to check whether or not the function is defined at x equals 3. And because it's a piecewise function, we need to know which part of the function to check. So this part of the function right here is for values from 0 to 3, including 3. So we are going to check to make sure that it is defined at 3 there. So g of 3 is equal to the square root of 3 plus 1, which is equal to 2. So criteria number 1 checks out. G of x is defined at x equals 3. Now, our second criteria is that the limit as x approaches 3 of g of x exists. So we've got to check the one-sided limits here. We've got to check both to make sure that they both equal the same thing. So again, what I like to do is set up an equation. I've got the limit as x approaches 3 from the negative side of g of x is equal to the limit as x approaches 3 from the positive side of g of x. And again, we need to know which function to use based on which side of 3 we're approaching from. So when we're approaching from the left or the negative side, we're going to use the square root of x plus 1. So we get the limit as x approaches 3 of the square root of x plus 1. When we approach from the positive side or the right side, we're using 5 minus x. Oops, make sure you carry down that negative next to the 3 for the one-sided limit. And again, both these limits can be evaluated by direct substitution. So we'll just come up here. And when I evaluate the left side limit, we get, again, 2. When I evaluate the limit from the right-hand side, we get 2 as well. So this checks out. We also need to write a quick sentence that says, thus, the limit as x approaches 3, no one-sided plus or minus here, of g of x is equal to 2. Again, you want to check the one-sided limits, but then you also want the AP reader to know that that means the actual limit exists. Third criteria, so this was criteria 2. Third criteria is to make sure that the limit is equal to the actual value of the function. So the limit as x approaches 3 of g of x is equal to g of 3. Then we can say, thus, g of x is continuous at x equals 3. So you need all 3 parts on your paper, and then you can write your conclusion. So function is continuous. We have that. Now we need to figure out whether it's differentiable. Now, a justification, again, we can't just substitute into the calculator, plug it in, and give that value, right? We need to actually go ahead and prove it using our definition. So part number 1 is easy, right? G of x is continuous at x equals 3. I guess I should say it's easy because we had to do the work in part A, but once we do all that work, we can just say g of x is continuous because we've already done it up above. Now, if they didn't ask you part A, if they just jumped straight into whether g of x was differentiable, you would have to go through the 3-part definition of continuity, right? We can't just put g of x is continuous at x equals 3 if we haven't proved that. But since we did the work for part A, we don't have to redo the work for part B. For number 2, or the second part of this definition, we need to show that the limit as x approaches 3 from the left-hand side of the derivative of g of x is equal to the limit as x approaches 3 from the positive side of the derivative. Right? So essentially the slopes of the tangent lines have to be approaching the same slope as you come in from the left and the right-hand side. So we now have to take some derivatives. I'm probably going to erase, in fact I am. I'm going to erase what I have for part A just to give us some extra space. Should have cleared this before I started this problem, then I could just do it in one swoop. But now I've got to erase everything individually. That's okay though. There we go. And I am going to write each step out. Oops, almost made a mistake. Make sure that is the derivative of g, not just g of x. So we also need to figure out which piece of the function we're supposed to take the derivative of. Again, we talked about this for part A. So we have the limit as x approaches 3 from the left-hand side, and we're going to need to take the derivative of the square root of x plus 1. That's equal to the limit as x approaches 3 from the positive side of the derivative of 5 minus x. So then we go through and we take these derivatives. By now we're getting pretty good at taking derivatives. I'm going to take this over here just to show you how I'm breaking this down to finding the derivative. So the square root of x plus 1, right? That's equal to the quantity x plus 1 to the power of 1/2. So if I then take the derivative of that, I'm going to get, using the chain rule, I'm going to keep my limit here though. That's going to be equal to 1/2 times the quantity x plus 1 to the power of negative 1/2 times the derivative of the inside, which is just 1. So in this case, we don't have to write anything. This is equal to the limit as x approaches 3 from the positive side. The derivative of 5 minus x is just going to be negative 1, so that's nice. These limits can be evaluated strictly by substitution, which is also nice. So I'm going to get negative 1 on the right side. On the left side, there are a couple of intermediate steps you could do. Let me just do them up here in orange. You can do them down there. You have a little bit more space than I do. Remember, 1/2 times the quantity x plus 1 to the power of negative 1/2. We can rewrite that as 1 over 2 times the square root of x plus 1. Again, pause the video if you're not sure how I converted the exponent to a radical. The negative exponent to a radical in this case. And then it's pretty easy if we substitute in 3 here. That's going to give us 1 over 2 times the square root of 4, which is 1 over 4. So this is a false statement, which means the limits of the one-sided derivatives are not equal, which means that the function is not differentiable at x equals 3. So we just say false, thus g of x is not differentiable at x equals 3, and we are done. If they did equal one another, then we could say true, thus g of x is differentiable at x equals 3. Okay, we're going to do one more problem. It is on the next page. So let me clear this. Slightly different type of problem, but still using the definition of continuity. Make this one click bigger. There we go. Okay, so now it says, for what values of k and m will the function be both continuous and differentiable at x equals 3? So you're not proving that it's continuous or differentiable, you're finding the values of those two variables that would make it continuous and differentiable. So we can assume that it's continuous and differentiable and just find the values that would work for that. For continuity, we are checking the one-sided limits of the original function, right? So we've got the limit, in this case, x is approaching 3, again, from the left, of h of x. That's got to be equal to the limit as x approaches 3 from the positive side or the right side of h of x. And just so we're all aware, this is for continuity. Okay, this equation would have to be true for the function to be continuous at x equals 3. Well, which part of h of x are we going to use as we approach from the left? That's going to be k times the square root of x plus 1. And as we approach from the right, we are going to use mx plus 2. Okay, so even though we have a bunch of different variables here, we can still use substitution to get two expressions for the answers of these one-sided limits. And here's what I mean by that. Let's first make this plus a little bit better. It could be confusing. That's not that much better. One more time. Okay, there we go. So if I substitute in 3 into both one-sided limits, start a different color, I am going to get k times the square root of 4, we'll simplify that in a second, is equal to 3m plus 2, which gives me 2k is equal to 3m plus 2. Now, just having one equation with two variables doesn't give me any way to know what those two variables need to be. But we do have another part of this question, right? It said the function had to be continuous, but it also needed to be differentiable. So let's start on the differentiable process and see if we can come up with another equation. So this next part will be making the function differentiable. So we have the limits of, or the one-sided limits of the derivatives this time. So if h prime of x is equal to the limit as x approaches 3 from the positive side of h prime of x. Now, again, same process. Make sure you know which piece of the piecewise function you need to use. As we approach from the left, that's of course going to be my k times the square root of x plus 1 is equal to the limit as x approaches 3 from the positive side of, you know what? I need to make sure I put my derivative symbol there. Let's go back. Can you take the derivative of this function? And the derivative of mx plus 2. You know what? I forgot the derivative symbol again. I'll tell you why I forgot in a second, but it's okay. There is no excuse. There's no good excuse. Okay, so why my brain was skipping over that derivative operator was because you don't have to include this step, right? If you just want to jump straight down to the derivative, that's fine. If you're taking the derivatives properly and you have the next step done correctly, the AP reader does not require you to have this step right here. I'm just showing you each and every piece of this process so that there's a clear connection. But as you become better at these problems, there are some things you can leave out and still have a complete body of work. So if I take these derivatives, we'll start a different color here, we have to treat the m and the k as constants, all right? Because they actually represent numbers. The variable x could represent a bunch of different numbers, right? But the constants m and k are only going to be one specific number. So they're treated like constants when we take the derivative. Thus, I'll do the right-hand side first because that's a little easier. We get the limit as x approaches 3 from the positive side. The derivative here is just going to be m, right? You could think of if we had 5x plus 2, the derivative would be 5. If we had 4x plus 2, the derivative would be 4. We have mx plus 2, so the derivative is equal to m. On the left-hand side, a little more complicated, but the k being a constant actually doesn't complicate this too much. So I'm just going to write down the derivative, and if you need to go back and look at all the work, you can. So we have x approaching 3 from the negative side. The derivative here is going to be k over 2 times the square root of x plus 1. So I encourage you to do that derivative work on your own, and then see if you can figure out how we got that derivative down there. If you end up getting confused at that step or on taking the derivative, you can always come to me with a question on that. Now we're just going to, again, substitute 3 in for x. So I'm going to come up here, and if I substitute in 3 in for x, I get k over, it's going to give me 4. I'm not going to write out every step because I'm running out of room, but it would be 2 times 2 in the denominator, which would give us 4. That is equal to just m, right? If there's no x, there's no place for me to substitute in a 3, and we're left with m. So now I have two equations with two variables, and this just goes back to basic algebra 1. I have a system of equations here, so I can now go ahead and try to solve. I'm going to use this equation up here, and I'm going to substitute in k over 4. You know what, it might be easier to get rid of that fraction first. So we'll say that k is equal to 4m, and we can actually use this one instead. You could certainly use the fraction, it's a little easier to not work with fractions. So if you don't want to, you don't have to do it. So I'm taking this equation right here. So instead of 2k, I have 2 times 4m. That's equal to 3m plus 2. That gives me 8m equals 3m plus 2. That gives me 5m is equal to 2. And m is equal to 2/5. If m is equal to 2/5, then I can come over here. K is equal to 4 times 2/5. Well, k is then equal to 8/5. So these two values for m and k, if we substituted those into the original function, and then we performed our 3-part definition of continuity and our 2-part definition of differentiability, we would see that they would both check out. So these values make the function both continuous and differentiable. This body of work, what I have on the screen, is what is necessary to get 100% on this problem. All right, you got to show the AP reader that you understand this limit equation up here and this limit equation down here. So one equation for the original function, one equation for the derivatives. Okay, we're going to cut it off there. We're almost at 20 minutes. There is another problem down below that's similar, just different functions. So you can take a crack at that. I hope you enjoy the rest of your day, and I look forward to seeing you next time.